Here we go. So it's always fun to watch you guys do this. In fact, one of the fun things to do at the test is watch each other do their hand gyrations when they're doing the right hand rule. You left-handed freaks are actually at a. Do we have any left-handed people in here? Oh, just Nick. Okay. Okay. Are actually at an advantage because you can do it. If you're left-handed, you can do your right hand rule and then write your answer and look at you. Okay. If you're right-handed.
We can learn the left-hand rule.
Crap. If you do the left-hand rule, you have to go in the opposite direction to the way your thumb points. Okay, you can do left-hand rule, but you just have to remember to go opposite. Here are your answers. You point in the direction of the velocity. The velocity is going into the page, but it curls this way, which means your force is... That's the direction of your force vector. Here, velocity is that way, but it's into the page. You curl that way, and your force is at right angles. This is a 90-degree angle here. This is your force. Okay. Over here, this is fingers are that way, curls up. Your force is to the left. Okay. And finally, Nick, thank you for stealing the thunder. The particle is moving in 180 degrees at 180 degrees to the actual magnetic field, and so sine of 180 is 0. Therefore, there is no force. F equals 0. There's no force on that object. Okay, so that brings us to our next topic for the day.
Is it lecture 2 or is it 1?
I'm sorry?
Is it still 1?
This is still section 1. Okay? Which is our magnetic force. Magnetic force on a current in a wire. So we're going to draw our wire. Okay, our current is that way. It is going to run through a magnetic field. A uniform magnetic field directed into the page, which is the language that they use on the test. You know, you have a current running through a wire that is passing through a uniform magnetic field directed into the page.
Oh my god.
Yeah. All right. Well, we know that for any one, the current's going this way, which means that the charged particles are really going which direction? That way, but they're negative, right? And so our test particle is really going that way. Okay, so all that stuff. Here's our particle, and its velocity is in that direction. Now, we've talked about drift speed, and we remember talking about that, where the conductivity of the material and the right, and we have the drift speed and the velocity of the particle as it wiggles in between all the atoms and that sort of thing. That's really it's those. What this winds up being is a summation of all of the drift speeds. Our velocity here is a summation of all the drift speeds of the particles. So what we're really dealing with here, if we're just going to consider one particle, we are dealing with a force equaling Q V cross B. Okay. However, here's our current, here's our field. If we're moving that direction, it goes into the page, then our force is going to be then that's our force. Yeah? Okay. Well, we're going to kind of rewrite this a little bit. That this guy's going to experience a displacement, say from here to here. And we're going to call it L. Yeah, the length of the wire through which it travels in the magnetic field. You guys with me there? Okay. Well, think about our units here. This is charge times meters per second. We can rewrite this as charge per second times meters. Yeah? So if we just look at any one particular spot, this becomes our current times the general displacement through, that our current is moving. Okay, times our magnetic field. And this is the actual force, F sub B, on current in a wire. But we take a look at this. Not like you're paying attention to anything else, but you get my point. We're going to make a big magnetic field. And we take a wire like that, and this wire has a current in it. And right up in this piece we have this little current is going to move a ds along that wire. Yeah? Okay. And as we curl along this wire, okay, we're going to look at this guy up here. This ds, instead of being a length, this now becomes an infinitesimal length, right? And we can sum them all up. Okay, that this little ds is going to give us a differential force equal to our current times our differential L crossed with our B. Yeah? Now, because this is a cross product, the order matters. But our integration, we don't want to include the B into our integration. We're going to leave it out here. But we're still going to integrate this. But as we integrate this, if we're traveling along a line, right? Well, if we're traveling along this line, then doesn't this just become delta S? Yeah? As we go, okay, it's our displacement. Our displacement from here to here is going to be that, right? If we sum up all of the vectors, the vector sum is going to be the total vector if we go back to our displacement. All right, so stop here for that. And this is just going to equal the length of our wire. Well, think about this one then. We have a new wire. Okay, and there's our new wire. This is a closed loop. Well, how are we going to write our integral if we have if this happens? Well, we get our force is equal to I. Okay, where before we've seen this where it's over the surface of something. You guys remember this? But if we're just talking about a wire or a linear thing, this is around a loop.
It's closed, right?
A closed loop. Oh, not plus. Oh, goodness, no. But ds is our displacement, right? The integral ds is our displacement. Well, what happens if we start here and we go around and we wind up back where we started?
Zero.
Our displacement is 0. Okay. So the force on a wire with a current running through this wire, okay, if it's a closed current and it's in this, in a magnetic field, the total force equals 0.
So
Okay.
it's path independent?
It is path independent so long as it is closed.
If it's not closed.
Okay, so like this one here, this would not have zero force. There would be force on this wire. So if you have a current, if you have a current that is traveling through the wire, but it's going from one place to another, then you're going to have a force on that wire. If there's no net displacement on your current, on your charge, then there's not going to be any force. And that is that.